Welcome back, ladies and gentlemen. We are in our third video for our physics class. Isn't that exciting? I can't believe you guys made it all this way. You guys lived through the first two. I'm so proud of you. So we are in our third. There's going to be one more after this for our prerequisites unit, and then we will move into real physics. All right, so today we're going to talk about some graphing things that I'm sure your math teachers did an excellent job, and you know how to graph hyperbolas and parabolas and ellipses and rational functions. But I don't know if you've ever graphed real stuff, right? Math is nice because it's in a nice vacuum. It's in a perfect world, unhindered by the bounds of reality. But in physics, we have this unfortunate problem where stuff we do has to relate to real life somehow. So we need to talk about a couple of little differences that we're going to be doing specifically in a science context for graphing. We're going to talk a tiny bit about statistics, which you've probably never actually taken. And then we're going to hand wave our way through it so we don't actually have to learn statistics, and we'll just get close enough for a high school physics class. If you're going to go on to be like a physicist, like when you grow up, you want to discover something new about the universe, and you're chasing that holy grail of having a unit named after you, don't do it this way, okay? What we're aiming for is good enough to get points on the AP test. Don't get me wrong. My goal is for you to understand physics, to be able to set up problems, to be able to solve problems, but I'm not going to teach you grown-up graduate level statistics because you don't need it yet. When you need it, someone else will teach it to you, I promise. Okay, so let's talk about this beautiful little sketch I've done just to, ease our way into the lesson. Sometimes when we're graphing stuff, it's really nice to have all these beautiful equations, right? Or when we're doing math, it's nice to have an equation because we can plug stuff in, we can guess stuff, we can do calculus to it and all that stuff. But the reason we graph things is because sometimes looking at all this stuff just makes you feel like this. You look at all this junk, you look at all these negatives and these decimals and these exponents, and you just go, like it makes you feel like that. But then you graph it, and then you get nice fuzzy feelings, just like this guy has. He's actually kind of mad because he went through all the work of graphing that just to get a meme. And I don't know, but something about this really, I think, captures the way you would feel if you did a bunch of work just to get a funny picture of Danny DeVito. But anyway, I digress. Let's go talk about graphing. All right, so before we do any practice examples, let me tell you the bullet points and the important stuff that I expect you to hit when you are doing your own graphs. And when I say I expect, I mean the AP test expects. So let's talk about just some of the things that you might not have had to do in a math class that you absolutely have to do in a physics class. The first thing that we need to do is make sure that we have consistent spacing of our axis numbering. This might be axes. Maybe I should make this plural. But if we look at our axes, notice we go plus 2, plus 2, plus 2, plus 2, and so on. Or plus 5, plus 5, plus 5, plus 5, etc. The space between these numbers needs to be consistent on the y-axis, and it needs to be consistent on the x-axis. And when I say space, I mean both literal, the physical distance on the piece of paper from that mark to that mark, and I mean the number spacing, how far apart this number is from this number. So we need to make sure that our graph is consistently spaced, which probably won't be an issue for you because you'll be provided graphs. On the AP test, they'll have a nice piece of graph paper for you. in this class, your questions will probably be multiple choice and you'll just click the right one. But the sentiment is still there. And we need to make sure that our numbers are spaced evenly. This might seem like common sense to you, but when I give you this, a data table, where you're expected to take data from an experiment and put it here, what I see way more often than not is kids will take these numbers and treat them as labels. So they'll go 10, 8.91, 6.22, and they'll use these as axes labels instead of just going 1, 2, 3, 4, 5, right? Your axis is like a measuring stick. You want your measuring stick to be regularly spaced and evenly incremented, and then you can use it to measure weird wobbly graphs, right? You want the graph to wobble, not your axis. Okay. The next thing we need to do is, in math, you don't usually have to label axes, at least in all the math that I teach. I'm sure it comes up occasionally, but it's never the main focus. And I think it's unfair to evaluate on something that no one has explicitly told you, here's how I want it done. So I'm going to tell you exactly how we're going to do it. The title of your graph up here, you have two options. You can do dv versus iv. When I say dv, I mean the dependent variable. Pendant. I hope that's spelled right. And then iv, of course, is the, whoops, hold on, spelling is hard, is the independent variable. I think it's dent, independent variable. Okay. We'll talk about more how to identify which one is dependent and which one is independent later. Usually it's determined by the way you measure things in your lab or your experiment. But it's pretty obvious. It's not too bad, right? The other way you can title a graph is y as a function of x. And when we say y and x, we mean whatever's on your y-axis and whatever's on your x-axis. So y in this case is position as a function of x in this case is time. I prefer this one because it makes a little bit more sense and it kind of harkens back to this from math, f of x, or f as a function of x. It tells you the thing that you're plugging in and the thing that's coming out. So I prefer this notation, but this has been kind of the gold standard for really lazy physicists for years. So, 6 of these, a half dozen of those. Okay. The other thing that I tend to see in this class is when people graph things and they're given just a blank sheet of graph paper, students really like to make graphs that look like that. So you have all of this paper and then your entire graph fits in this tiny little section, and you've got all of this blank canvas just yearning to be drawn upon. And it looks sloppy. It's less accurate, especially if you're doing things by hand and you're trying to draw best fit lines, which we'll talk about in a couple of slides. And it's just a waste of paper. You know what I mean? People chop down entire rainforests just for you to have a nice slice of paper, and you're going to waste it like that? It's shameful. So when you're drawing a graph, do me a favor. Use the whole graph. Okay? We have a light rule of thumb. Use 80% or more of the graph. And you're going to say, Mr. Barton, how do you define 80%? I'm going to look at it, and I'm going to search my soul, and I'm going to say, does this feel like 80%? And if I say no, then it's not. And that's as qualitative as we're going to get with that. But you get what I'm trying to say. You want your graph to take up most of that stinking graph. Don't make it a little namby-pamby baby graph, right? Use that paper. We already chopped down an entire tree for you. Use it. The last thing is when we label our axis, right? We have to say what is on this axis. Position. you're going to put what units you measured the position in right next to it in a little set of parentheses. So our position here is in meters, and our time here is in seconds. Okay. So there's 4 things we need to be aware of. Axis spacing, DV versus IV title, use the whole gosh dang graph, and make sure you've got units on your labels. All right, let's go practice that, shall we? Okay, here's a beautiful graph. I recommend that you pause the video and draw one of these. If you have a ruler, that would be even better. I'm going to even go so far as to recommend that you beg and plead with your legal guardian to go buy you that really, really nice notebook paper, right? But instead of just being lined notebook paper, if you search far enough, you can find graph notebook paper. And this stuff is the bee's knees. This stuff really just tickles that sweet spot of having literally everything you could ever ask for. It makes it so easy to graph. It makes it really nice for consistent. It's, I kiss my fingers if you couldn't hear. So let's go ahead and make this graph. Here's our data table. When you are reading data tables, the first column is almost always your independent variable, and then the other one is your dependent variable. The other dead giveaway in this case for us is, do you see how these numbers follow a pattern? +1, +1, +1, +1, +1. And these ones are real random and ugly. The nice pattern one is your independent variable, and the ugly ones are your dependent variable. Okay. So let's go check that checklist, shall we? All right, consistent spacing of a numbered axis. So let's number this axis, shall we? For my dependent variable, which is going to go on the y-axis, the thing I'm measuring is going on the y-axis. I need to go up to 10 and make sure I can go down to -1.9. So this goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's just go by 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 plus 1, and then -1, -2, -3. All right, so we know we're going to have something that starts here, goes down to almost there. We're going to be filling in this whole section of the graph. That looks like it's going to take about 80% of the space to me, so that looks nice. I like that. Okay. Whoops. There we go. And then for our independent variable, or the x-axis, we have to go from 0 to 6. 1, 2, 3, 4, 5, 6. Sweet. I'll admit that I have a slight advantage here because I drew the axes myself, and I wasn't given a pre-printed graph. If you had something that looked more like this, where it was a lot more condensed and squished, what I would do is I would count up how many total notches I have and then divide by the number I'm trying to get to. So let's say there were 18, right? 1, 2, 3, 1, 2, 3, 6 times 3 is 18. So let's say I had 18 and I divide by the number I'm trying to get to. That'll give me, not 6. Try again, Mr. Barton. 3. This will tell you, all right, every 3 tick marks, go to the next number. And then that'll be a pretty good way to space out your graph so that it takes up most of the space and it's evenly incremented. Okay. All right. So we have our axes evenly incremented. Check mark. That bad boy is definitely going to take up at least 80% of the graph because we made our axes nice and spaced out. All right, let's put a title on it, and we have to put some axis labels. So title, we can do DV versus IV. That would look like speed versus time. This would be a perfectly acceptable title for this graph. This would get you full points on your AP test if that's what you're really worried about. And this would be acceptable pretty much all the way through an undergraduate degree. So you're going to college and you have a bachelor's degree in physics. They'll take this pretty much all the way through that. Once you start trying to get your PhD, you might want to get a little more creative, but until then, you're fine. Just follow the formula. The other way that we could title our graph is y as a function of x. Y is always your dependent variable, and x is always your independent variable. So it would be dv as a function of iv. So we could say speed as a function of time. Here, and then let me fix this so that your English teachers aren't appalled when they see it. All right, so speed as a function of time, that sounds a lot prettier to me, but I'm a little biased. I tend to favor colorful language, and the dv versus iv just doesn't really quite do it for me. So I'm going to leave it as speed as a function of time. Now we need to label our y-axis and our x-axis. Our y-axis is always going to be our dependent variable, and our independent variable will always go on x. So our y-axis is speed in meters per second. Make sure you put the units in parentheses. And then our x-axis is going to be time, and we're going to measure that in seconds. All right. Then at this point, we can go ahead and just throw these points on here as best we can. Of course, you'd want to use a ruler or maybe even some really nice graph paper. I'm going to do my absolute best here, but you're going to, I'm not perfect. You can't expect that of me. So there we go. There's that. 2, we have to go to 6.2, so we'll go up to 6, and then maybe a little bit. Keep in mind, this is high school physics. It's really just 6.2. Do your best. 6 and a little bit, right? 4.75, so 4 and then 3/4 of the way to the next one. Maybe about there. 2.63, so 2 and a little over a half. Maybe right there. 0.90, so almost 1. Oh, I've missed one. Luckily for me, I'm on a smart notebook, and I can just scooch those right over, right? There we go. And then 6, we have to be at negative 1.9, so we're going to be at almost negative 2. Okay. Because on the AP test, you are definitely going to be doing this by hand. They're not going to give you a computer with an Excel sheet to make it really nice and exact. That's about as precise as you have to be. When we say negative 1.9, we mean almost negative 2, right? That's about as precise as you have to be. No one is going to crucify you if you do negative 1.92 instead of negative 1.91. There's an understanding that because you have to do it on a piece of paper with your hand, that it's not going to be absolutely perfect. Just do your best. All right. Let's talk about this thing called a best fit line. In real life, you're going to collect data, and it is absolutely never going to be as perfect as it would be in math class. In math class, you'd have a nice formula. You'd say y equals 3x minus 2. You're going to know that's going to hit exactly at negative 2 on your y-axis for your y-intercept. And you know your slope is going to be exactly 3. So you're going to go up 3 and then to the right 1 unit every single time. When you collect data, let's draw a perfectly straight line through this stuff just to see how not perfect it is. Do you see how we're missing all these points? This is much more like real life. So what we do is we create what's called a best fit line. And a best fit line is kind of like an average line. It's the best approximation. It'll get us pretty darn close to our data points, but there's an understanding that because real life is dirty and messy, it's not going to be perfect, but we do our best. So here are some guidelines on how to make a best fit line as accurately as possible. So the first rule is you should have an equal number of points above the line and below the line. Okay. Keep in mind there are 3 tips here if you just use this one. If we look at this, there's, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points. So let's go 1, 2, 3, 4, 5. We'll go right through 6 so that it's neither above nor below. This red line technically satisfies that condition. But you're going to say, well, that doesn't look anything like this data. And you're right. That's why we have the other 2 conditions. So the next one, this is a real statistics rule. If you wanted to calculate the exact best fit line, like you want to calculate it, you didn't want to guesstimate or hand wave any of it, your line has to go through X bar, Y bar. And let's talk about a little bit of notation. X bar, this is the fancy math notation for the average of the X values. Okay, so anytime you want to say the average, right? The average velocity, the average amount of money, you put a bar over it. So if we take all the X values from this point, this point, this point, and so on, and average them together, you're going to get something pretty close to the middle, because this goes to 10 and this is 0. I'm going to give you a pro tip, and the average is definitely at 5. And then you do the same thing with your Y's. Here's 4, here's, I don't know, 23. What's the average of that? Whatever that is right there. So if you average your X's, you'll get an X value. If you average your Y's, you'll get an average Y value. And if you make an ordered pair out of those 2 average numbers, your best fit line is guaranteed to go through it, and that's a rule of statistics. There are other rules to tell us the slope of this, but we're not going to learn them because the formula is super ugly and we don't want to mess around with that. But taking an average of things is pretty easy, so we can include that. Then we want to try and minimize the distance of all the points. So we know that we want half the points above the line, half the points below the line. It should go through this point and then minimize the distance. This means eyeball it and draw it as close as you can to as many points as possible. Usually what will happen is you'll have what's called an outlier, and you'll have one point that kind of hangs out there and isn't super close. That's understandable. That's fine. But really what we're saying is don't try and satisfy this first condition and just draw it like this. You want to try and make this line as close as possible to all of the points at the same time. Okay. And then those 3 rules will pretty much get you through this class and maybe your first year or 2 of college. After that, they teach you the formula to do this minimization, and they kind of expect you to use it. But for right now, that's not our problem. All right. So let's go ahead and try that out on our graph right here. Let me go ahead and copy these points that I've already pasted on there. So let's grab those. All right, sure. Let's copy these. Copy. Paste. Oh, check that out. And then we'll try and grab all these points here. Copy that. Paste. And you guys can go ahead and just copy and paste that on your notes as well. I love that joke. That joke never gets old. Okay. So here's our data. I went ahead and gave us X bar and Y bar. So our average X, if you take 0, 1, 2, 3, 4, 5, and 6 and average these, meaning you add them together and divide by the number of things, you'll get 3. If you do the same thing here with your y values, you'll get 4.321714, blah, blah, blah. We're going to say this is about 4.32, which means about 4 1/3-ish. Okay. So we want to go put this point here, 3, 4 1/3. We're going to go put that on our graph, shall we? So 3, 4 1/3. That's pretty darn close to that. I'm going to do this one in, let's do purple. I think maybe a tiny bit under that. Oh, no, actually it should be a tiny bit above that, right? Because that point is 4.2. So it'll be just above that purple one, or that blue one. There we go. Now, we want to draw a straight line through these points where we have as many on the line as possible, and a few, couple above, couple below, hopefully an equal number of both. So let's draw our line. A hint that I like to use is if you know your y-intercept exactly, you know exactly 0, 10, I generally like to make it touch that point. Like if this is a measured point that you collected data for and you know every single time at 0 seconds you are going 10 meters per second, go ahead and make it hit that. Then we're going to aim for that midpoint. And there we go. So we've got 1 above, 1, 2, 3 below, maybe not quite. That's the problem with picking a fixed y-intercept. If we tilt this a little bit up, and then maybe tilt this one a little bit down so it goes back to that midpoint, you see how it gets a little bit better? So half of these, or what's the saying? 6 of these, half dozen of those. Anyway, that's going to be our best fit line. It is important to be able to find the equation of this line. If I were going to find the equation of this line, our goal is always to have a linear line. So it'll be y equals mx plus b. We know this b value, right? It's a data point. It's right there. When I'm on the x-axis, we're at 10 meters per second. So I would just go ahead and be feeling great about saying b equals 10. X and y are variables. We might want to use some real physics variables instead of x and y. On our y-axis, we have speed in meters per second. So we might put a capital S. And on our x-axis, we have t for time. In physics, the variable for time is always a lowercase t. And now the real cryptic part of this problem is our slope. So let's talk about the slope really quickly. To find the slope of this graph, on the AP test, they're going to give you a much finer graph, meaning it's going to be chopped up a little more evenly like this. What you would want to do is find 2 places on your graph where your graph does this, where it goes exactly through the grid of your graph paper. So you're going to have something that looks like this, right? And see, it doesn't really hit the corners exactly, but right here it does. So I would take this point, and then we'll pretend it hits there at 10. So I would take these 2 data points. I would take 3, 4.33, right there. And then I would take 0, whoops, goofed there. I would take 0, 10. And then we would go ahead and use our slope formula to calculate the slope. So let's go ahead and do that. Our slope formula is m equals y2 minus y1 over x2 minus x1. The other way I like to think about this is y final minus y initial, because in physics we often want to distinguish between where we start and where we end. So final and initial are sometimes a little bit better than 1 and 2. So we're starting at 0, 10. So our starting x would be 0. Our starting y would be 10. So we'll fill those in. Minus 10, minus 0. And then our final would be wherever that point that you're trying to end at or aiming for is. So our ending x in this case would be 3. I understand we go for 6 seconds, but this is just the later point of the two we're using. And then our starting y is 4 1/3. Okay. So we do our subtraction. 4 1/3 minus 10 is negative 5 2/3, or negative 5.67, over 3 minus 0 is 3. And then we could just throw this thing in our calculator. So we'll grab our calculator and we will type in 5.67 divided by 3. We'll get a decimal to about 2 decimal places, and we'll get negative 1.89. So there's our slope. We're losing about 1.89 meters per second every second. Not too bad. All right, so I hope this helps with getting you started for your graphs. We will go over this more in depth again once we start doing lab reports. But I think it's important to get your feet wet with this before we dive into a full formal lab report, because if you don't, it can be a little bit overwhelming. So if you have any questions, or if you think I'm being a little too wishy-washy about this, go give me a piece of your mind in the WebEx. Or better yet, like and subscribe. I'll see you next time.